thank you all for coming, and I mean, thanks to the organizers for. It's good to see that we're 4 organizers here and about 4 participants. That makes it feel quite a.
You know your fellow organizers.
Yes, exactly. So yeah, what I want to talk to you today about is joint work with Andrew Duncan from Imperial College and Radek Erban from Oxford, and it relates with hybrid modeling of stochastic chemical kinetics. So I guess, I mean, I'll give it almost like a normal talk, but I'll just speed up a bit when it comes to the intro. So yeah, I mean we have the introduction, which is just basically gonna be centered around why stochasticity perhaps is important in specific systems, and then what I'm gonna try to do is basically follow the physicist approach and then the mathematician approach. I'm somewhere in between, but basically using just a heuristic argument, I would be able to explain how we derive this jump diffusion model that I want to talk about. And then for people that are more mathematically inclined, and hopefully they were not going to ask too many questions, I'm just going to give them a theorem about the large volume limit that explains the behavior of our jump diffusion model. Then I'm going to talk to you about 3 different numerical algorithms that one can use in order to simulate this model, and then go into some different numerical investigations that we've done. And by all means, if there is something that you don't understand, or if you would like to comment on something, just interrupt me. And also, if there is any sort of, I think we've done quite a lot of numerical investigations, but if there is something that you think it would be interesting to looking with this model, please go ahead. And then, I mean, in terms of conclusions, I mean, in some sense, I'm going to tell you a few where we would like to take this. I mean, we have already been discussing with Radek about a few possible extensions, but again, it's kind of brainstorming. Any kind of idea is welcomed. So yeah, I mean, this is the typical stuff, which, I mean, again, I'll just read a few of these bits, but I guess I'll try to speed up going through that. So chemical events and some binding and dissociation occur at random times. This leads to fluctuations in chemical concentrations. These fluctuations are called internal or intrinsic noise. And in principle, if you are in a situation where you have a large number of molecules, this intrinsic noise is not important. But then in cases where you have a system that has low number of molecules, such fluctuations can have a significant effect. Okay? I mean, this is a picture taken from this paper, and it sort of kind of shows, I mean, one of the possible effects of intrinsic noise. So here we basically have the solution of the ordinary differential equation. It just goes up and then it goes down. But if we were to kind of model the same system with stochastic chemical kinetics, even though we would be in a parameter regime where the ordinary differential equation would not allow for oscillations, this is basically what happens when you simulate things stochastically. So these are kind of a few of different effects that intrinsic noise in chemical systems can have. So, I mean, just to set up the scenery a bit in how we describe a chemical system, this is our typical, this is one way. I have n species interacting through m reaction channels. This is one particular R reaction channel. This is one particular reaction channel. So this is, these coefficients here tell you how many the number of molecules of x1, x2, and xn involved in this reaction, and then the numbers that you have here tell you how many molecules you have after this reaction occurs. Okay, and the typical assumption, and David gave a very nice tutorial about that, so I'm not going to dwell on this too much, is that we assume that this reaction happens with probability lambda k x of t times delta t, where lambda k is the propensity function of this specific reaction. Okay, and if you want to understand how much a species changed by its reaction, then you just need to look at the stoichiometric vector. Okay. So in terms of, I mean, this is, we all know that this is basically a stochastic process. So what I'll try to do in the next 3 or 4 slides is basically give you the picture of the duality between the master equation and the paths level. So given that this is a stochastic process, you need to write down a differential equation, perhaps a difference equation, a PDE that tells you how the probability of being at a specific state at time t changes with time. So the system that I just described is a Markov jump process. So the corresponding master equation is called the chemical master equation, and basically is given by this. It's if you like a system, an system of infinite ordinary differential equations. So, and some people like to have tried and tackle trying to solve this directly by, for example, imposing a maximum copy number for each species, having a finite system of linear equations and try to solve that. But in general, this is not tractable, and you have the so-called terms of dimensionality, because the size of the available state space grows exponentially with n, where n is the number of chemical species. So, in my caricature,
I mean, there was like Christoph's talk at the workshop, and I see once in a while other people are trying to do smarter ways to solve the chemical master equation. I mean, what's your sense of the progress in that area? Is that getting reasonable, or is it still kind of far from satisfactory?
I mean, I think it's as difficult as solving a high-dimensional PD. So I don't know of. I mean, I know of the early work. I don't know how advanced current work is, but I mean, it's as difficult as solving a high-dimensional PD, which is quite a difficult thing. I mean, I know of a few people coming from sort of like chemistry background that they have tried to use these tensor decomposition ideas, and they claim that it works very well, but I'm not really sure. But I mean, in some sense, the way, I mean, what I like about stochastic processes, or the way I like to think about them, is the fact, okay, you can write down your master equation, you can write down your Fokker-Planck equation, and you know, if you want to deal with the problem on that level, you can do. If you don't want to deal with the problem on that level, there is always the duality of what happens on the path space. So, and I mean, that's more or less what I was doing on my PhD as well, so this is the kind of thing that I'm comfortable with. So, I mean, this is the basic Gillespie algorithm. And this is a corresponding path representation. I mean, as I said, this is a Markov jump process, okay? So you can write down explicitly the equation that being satisfied on path level from the stochastic process that I just described poorly here, okay? And in terms of what this is offering you, I mean, you know, on the master equation level, you have the system of infinite dimensions to solve. What you have here, I'm not saying that it's easier, but it's kind of something that you can understand a bit better, at least in my way of thinking. You basically can generate a lot of paths and try to build the probability distribution from that. And this is basically the simplest algorithm to do that, which you've already seen. I'll just say that, you know, you basically toss two coins at each time step of the algorithm. The first coin tells you when will the next reaction event happen. The other coin tells you which reaction event is going to happen. But basically, once you're able to write this thing down, as David very explained us very well, and in the opening workshop, you can basically try to use this Poisson formulation in order to come up with different algorithms that they would be exact, like the Gillespie algorithm, but which perhaps, I mean, as we saw, for example, when it came to try to do multi-level Monte Carlo, are more natural ways of expressing these equations. So I kind of feel bad trying to explain this, because I sort of understand it, but I'm probably going to do a terrible job explaining it, but I'll still try. But let me just write something on the board as well that is going to be needed for later on, okay? Okay, I'll explain in a second what this is. Basically, each reaction can be expressed as a time change of homogeneous Poisson process. So each reaction, if you like, has an internal clock given by this TRT, okay? And with respect to this internal clock, you kind of ask when each individual reaction will fire. And because, you know, this is, I mean, after you make the change of variables, the change of time, all the Poisson process are kind of run on the same time, the time for the next reaction for each one of them is basically just distributed like minus log of u. Okay? So if fr star was the time that the last PR event before time t happened, the next jump time would be this plus this time. So that means that the next reaction occurs. So when it comes to looking at what happens in the internal clock, you have the following thing here. But basically, because you have you have this time change, if you think about in terms of the actual time, what that means, you have this equality here. Essentially, you're solving this ordinary differential equation. But now, because your Poisson process doesn't change between different times, actually you can solve this differential equation exactly, and basically combining all that stuff tells you when the next R reaction occurs. Okay? So this tells you individually what happens on the level of each reaction channel. With a bit more thinking, you can write down the next reaction method. And in some sense, one possible advantage of that, besides the multi-level Monte Carlo, which, I don't think that it's really why you would like to use that. Basically, you only need to use one random variable at each time step of the algorithm, basically. So, more or less, you do this for each of the reaction channels, and then you kind of pick the smallest time, because that's telling you when the next reaction is happening, and then you have to update your system accordingly. Okay? So the reason why I kind of talk about these algorithms, about these two algorithms, is two of the three numerical algorithms that I'm going to talk about the jump diffusion model are going to basically be based on the Gillespie version and on the next reaction version. There's going to be an added caveat, and that's the reason why I've written this down. So I'll come back to that. I'll come back to that when we talk about this in a bit more detail. But there are cases but in our jump diffusion model, basically we are not necessarily able to solve this equation exactly. So I'll come back to that, and in order to deal with that, we came up with a third algorithm. This is basically everything I discussed so far is about discrete time, is about the jump process, the Markov jump process. In the case where the large system volume size, you can apply the so-called diffusion approximation and obtain the chemical Fokker-Planck equation. Again, I'm not going to dwell too much on that. It also suffers from the curse of dimensionality, but because it's actually a PDE, people like Radek and other people kind of feel more comfortable with that, and they have proposed a few different things about how to solve this. But basically, again, now what I'm doing, I have my jump process. I'm approximating in some sense from a continuous stochastic differential equation. This is what happens on the level of the master equation. We just call it chemical Fokker-Planck, because normally you call Fokker-Planck the master equation for an SDE, and then chemical because we're trying to describe a chemical system. On the path space, basically, this is the master equation for a stochastic differential equation that looks like this. Okay, and a very simple way of solving this equation is to using the Euler-Maruyama method. Okay, I'm not going to be talking about Euler-Maruyama anymore in the talk. I'm actually going to talk about the method that we used is a method proposed by Dave. Let me just say a possible issues with the CLE. First of all, we know that it's not a good approximation for small numbers. So, in some sense, you don't want to be doing this when the copy numbers are small. Another issue with that is that solutions might actually become negative. On the level of the chemical master equation, there is no probability of becoming negative unless you put some boundary conditions for the chemical Fokker-Planck or some reflecting type of conditions on the level of the SDE. You might become negative. Another big issue is that exit time behavior might not be correctly captured, and I'll come back to that in the numerics. This is basically. We've discussed a bit with David while we're here about the chemical Langevin equation, and actually if it makes sense to use the chemical Langevin equation. This is, in some sense, I'm still thinking about that, but what I will say is that the thing that we're basically going to discuss today, if you like, is the correct way to do the chemical Langevin equation. Now, if you think that there is point to doing the chemical Langevin equation, that's kind of a separate question. For the time being, let's accept that this is the case, and let's just see a way to overcome some of those difficulties.
So CLE and CFPE, are those equivalent?
Yes, it's like a stochastic differential equation and Fokker-Planck. I mean, the three just comes, yep. I guess.
If you have a large numbers, can you say that the CLE is a good approximation at equilibrium, or even there you might have issues? So on
I think even
time horizon.
I think even there, I mean, as far as I know, that all the results that they prove that it's good in the large volume limit, they're for finite time. And actually, the result that I'm going to talk about here, it's also valid at finite time. Even though, you know, when we do the simulations, we don't see too much of a problem. I think actually Andrew Duncan is working on looking at what happens at infinite time. Okay, so now it's the part of the talk that I really enjoy because it's the actual idea. So I said I want to essentially couple. I want to couple the chemical master equation with the chemical Fokker-Planck, or if you like, the Poisson representation with the stochastic differential equation representation. So let me just do it in one dimension, okay, and just explain what we're doing here. So I'm just basically introducing a function beta x, okay, and this is OA, OB, OC, okay, in which I'll just draw. It starts with 1. In this part, it goes between 1 and 0, and in this part, it's at 0. I mean, I can think of other interpolations as well, but I'm sort of just doing the simplest one. And what I'm doing, I'm basically write 1 equals to 1. Okay, I'm taking my propensity function lambda j, and I write like beta x times lambda j of x plus 1 minus beta x lambda j of x. Okay. So let's go to the chemical master equation, okay? And basically, if I denote by beta tilde equals 1 minus beta x, then again, I have just written my chemical master equation in a slightly different way, okay? But surely, because beta plus beta tilde is equal to 1, there is no approximation. I mean, it might seem a bit obnoxious for doing that, why I'm doing this, but I'll try to explain it. In the next slide. I mean, and again, this is not the way we're doing it in the paper. This is just to give you the heuristic of why, of how did we come up with this. So, okay, one of the ways to get the chemical Fokker-Planck from the chemical master equation, I mean, if you don't care too much about large volumes and things like that, you say, okay, I perform a Kramers-Moiré expansion, I keep the first two terms, and then I throw everything else out. Okay. And that's exactly what we're going to do, but we're only going to do it with respect to the part of the chemical master equation that has beta tilde. Okay? So if you are to do this, and again, close a bit your eyes and sort of like have faith that this would be a reasonable thing to do, then you end up with this kind of mixed system. Yeah, if you like. This is I mean, it doesn't have to be, but it turns out that this is the master equation for a jump diffusion process. Basically, and you know, the diffusion, the drift and the diffusion of the continuous part is exactly what you would have from the chemical Langevin equation, but it's kind of discounted by this beta tilde x. Yeah. So actually, there are parts of the state space for which this is completely equal to 0. So you're doing complete jump diffusion. There are parts of the state space where these are completely equal to 0. So you're just doing continuous approximation. And then there are parts of the space where you're sort of doing both, okay? So, I mean, so what I did in here, okay, I used one blending function for all the reactions. In principle, there is nothing that's stopping you for doing that for each individual reaction, okay? So now instead of doing it just for lambda j equals beta x, I do lambda j equals beta jx. Again, the same equality, and that basically, on the level of the paths, it gives me the corresponding jump diffusion process. Okay, so if you like, this and this are the things that you would normally have in the chemical Langevin equation, and this would be the things that you have on the level of the Markov jump process. Okay, so this is basically, if you like, I mean, when we started this work, we were kind of thinking of it as a numerical method for solving sort of like chemical systems. In some sense, without trying to beef it up too much, this is, if you like, a new model, or that lies just in between chemical Langevin equation and chemical master equation. Yeah, it's sort of like blends the two models. I claim, I mean, that's my claim in a nice way. I'll try to explain that. I'll try to explain that later on. So you can think of it as, okay, now this is the true. This is my new stochastic process that describes what happens in my chemical system. Okay, and then the rest of the talk is essentially how can we actually simulate trajectories from this thing, and then show you a few numerical simulations that exhibit that, at least for the system that we looked, is very reasonable and it works. It's almost as good as SSA, and it seems to be faster, even though, I mean, that's sort of debatable as well. Yes.
What's the tilde on the lambdas? Did you say that? Maybe I missed it. The tildes.
Well, in principle, I mean, I think you could just, I mean, for the time being, you can ignore it. It has to do that you kind of have to extend the. It has to do with the extension of the propensities. Yeah.
They were only defined on integers or something.
Yes, exactly, and that's why in here as well you sort of have.
Yeah, you know that makes sense.
Can Z go negative then?
No.
So, but you can get like Z is a half.
Yes, you can get Z as a half.
So that you prevent it from going negative.
Yes.
So what prevents it from going negative?
Well, you kind of, I mean, you could in principle have something being sort of like minus 0 point something, but as far as the propensity function cares, this is treated like 0. So it cannot escape on that part of the domain.
But there's two questions, right? So that model, Z cannot go negative.
Yeah.
But you're going to discretize that model
Yes.
and use a numerical method. And of
Yes.
course, theoretically,
Sorry, I don't see why can't the dw term make you negative?
Because this thing, while your Z becomes closer and closer to 0, this is turned off, basically. So essentially, you kind of push the boundary away. I'll come back to the. I mean, you're right about the comment about the numerical scheme, but again, if you're being careful, I mean, we didn't see anything like this. But
nor will you, and if you run it for the age of the universe, I think, right? I mean,
yeah.
We need a pretty big outlier from a normal distribution.
Yes, exactly.
I'm just trying to.
Yeah. No, but in some sense, even if this happens, I would like to think, but I need to think about it a bit more. When it comes to calculate what happens in the next reaction, that bit would have been switched off, and then it would be treated like you have 0 molecules. But yeah, I mean, it is still a possibility. But as a model, it cannot. I mean, you don't need to impose any conditions in principle, if you like. Yeah, this is a stochastic differential equation or a jump diffusion that never goes negative, basically. While in the chemical Langevin equation, you need to impose a reflecting boundary condition. Okay. I mean, if you were to think about it, about the chemical master interpretation of that, if you were to write the system, I mean, back here, these things here go to 0 as you approach the boundary, and this would ensure that you don't become negative. Yeah, I agree that then if you kind of, on the level of the simulation, something might go wrong, but on the level of the model, I would like to think that nothing can go wrong. Okay, and just to give you an idea of how the path of this jump diffusion looks like, it's kind of funny because it's really, I mean, there are really parts of the domain. I mean, in here I have used exactly the same blending function for all the reactions, just to help the illustration. So in this part of the domain, my blending function is 1. In this part of the domain, my blending function goes between 0 and 1. And in this part of the domain, my blending function is 0. So in this part of the domain, I have complete discrete jumps, okay? In this part of the domain, I sort of diffuse around, and then at some point, I jump, okay? And in this part of the domain, I just diffuse, okay?
I'm not seeing discreteness in the middle part,
It is discrete.
in the middle of domain.
Well, it is both. It's discrete and I mean, what in the middle part, you see it goes around, okay, and then at some point it jumps. The red bit indicates a jump. Okay? It's not discrete in the sense, you're right, that you still have your path here, but at some random times you are allowed to jump, if you see what I'm saying. Okay? I mean, I'll come back to the numerical methods. I mean, this is a particular choice of the blending function. Actually, for the numerical implementation, we kind of use, just the simplest one that we had there. Okay, so you can define a blending function for each individual. I mean, if I just had only one species, this would sort of be like my blending function, and then when I have more than one species, I'll take this to be involved in a reaction, take this to be the blending function in that reaction. Okay. And in terms of going back to Sam's question, in terms of theorem, if you now compare how this hybrid model behaves in the large volume limit versus the chemical master equation in the large volume limit, you basically, you see, this is, I mean, you see this, you obtain the following result for their scale processes, and you see this is valid up to time capital T. Okay, but basically what you obtain is that these two models in the large volume limit are epsilon square close together, which is exactly the same thing that you would actually get if you were to compare chemical Langevin equation with Poisson process in the large volume limit. The thing is, I mean, this constant C in our case should be smaller if you look at the proof, but we haven't really quantified how much smaller this should be. But now in the numerics you will see that things are behaving quite nicely. So in terms of the numerical algorithms, I mean, let's basically, let me see, which is, okay, let me start with the simplest one, which is basically the Gillespie version. I thought I should have them the other way around. Okay, so I have three time steps, if you like. I have a time step little delta t, which is actually a macro time step, so we should make sure that we change it, and I'm sure the referees will complain about that. So these are time steps that relate to the chemical Langevin equation. I basically check if all my blending functions are equal to 0, that means that my model is pure continuous model. Okay, so I can simulate the chemical Langevin equation using a macro step delta t. Okay, now if all of my blending functions are equal to 1, that means that I have no continuous part. Okay, so I do my Gillespie as I would normally do. Okay, otherwise, if I am in this intermediate regime, I calculate the time to the next reaction, and then calculate which reaction happens, and actually compare. If the time to the next reaction is smaller than the time step that I've used for my chemical Langevin equation, I basically simulate my chemical Langevin equation up to this, and then add the jump. Okay. Otherwise, if the time to the next jump is after the time step that I've chosen for my chemical Langevin equation, I just simulate my chemical Langevin equation up to the time delta t. Okay. So this is, if you like, kind of the easier version. This is how you will do the Gillespie algorithm. In the terms of the next reaction method, I mean.
Why do you have small delta and capital delta?
Well, it should really be the other way around, but in principle it could. I mean, you don't need to, but the idea is that, you know, if you are in parts of the domain where you're only doing chemical Langevin equation, you might want to use an even bigger time step. Okay, and that's why I'm saying it's kind of funny that we've called this little delta and this is big delta.
But you're saying that for the different domains you have a different delta.
In principle, you can have. You don't need to, but you can have. It's just a choice, basically. I mean, I mean, as a user, you give little delta t and you give capital delta t. But what I'm saying is that little delta t should be big delta t, and big delta t should be little delta t. In some sense, if little means smaller and big means larger. Yeah? In principle, delta t, I mean, you could choose delta t to be equal to capital delta T, but in principle you would like to think that this delta T is bigger than this delta T.
So in this mixed region, you're simulating the chemical Langevin equation. And you're keeping the intensity functions for the jump process fixed, even though, so there seems to be another approximation going on.
Yes, yes,
That's interesting.
yes, there is. I mean, this is not going to be exact.
No, I'm
Yeah.
trying to parse it, yeah.
So the next level of complexity is how to do it with respect to the to the next reaction method, and basically there, if you think about it, in the mixed region, okay, let me just put a lambda prime now to denote of x the beta x lambda x, okay, but also on top of that you sort of have a stochastic differential equation, the chemical Langevin equation involving the coming from these propensity functions. Yeah. Does it make sense what I'm writing on the board? I'm sort of saying that before, when I want to describe the next reaction method for the purely discrete system, this was the differential equation that I was solving to find the time, the time to the next event, and nothing was happening to this one because it was frozen between reactions. Now, I basically have as David well spotted, I have a Poisson process that changes with time. Okay? The intensity here changes with time in the part of the domain where I have both chemical Langevin and chemical master equation. Okay? So in that sense, this algorithm is even less exact than the other one. If all the blending functions are equal to 0, I do chemical Langevin equation. Otherwise, I calculate the time to the next reaction. Okay, if all of the blending functions are equal to 1, then I just do the next reaction method. Otherwise, I simulate basically the chemical Langevin equation up to. Otherwise, again, I need to check if little t is less than delta t or otherwise, and this is basically what I'm doing. But in some sense, I mean, because now x of t is not frozen between reactions, I basically have to make a choice of how to solve this differential equation, and in that I'm solving it with the Euler method. Okay. There is this thing called the thinning method for simulating non-homogeneous Poisson process. And this is basically the third algorithm. And in that sense, the reason why we introduced that, it's a way to circumvent this problem of having to approximate this differential equation. So the caveat there is that in principle you need to know that the propensity functions are bounded from above, from some number. But once you know that, and this could be the case in a system, in a chemical system where you know a priori an upper bound, okay, you can basically do this accept reject thing, which relates with the thinning. I mean, I don't want to dwell on this too much. We can discuss after the talk, and basically allows you not to having to approximate the solution to this differential equation. In some sense, you solve the differential equation exactly. And the kind of logic behind this is, as David pointed out, because you are not being exact here. In some sense, if you want to talk about the accuracy of the method, you always kind of no matter how clever you are with everything else, you would always have to deal with the fact that you're not solving this equation exactly. So this thinning idea in cases where you're able to bound the propensity from above allows you to kind of at least not having to deal with this error when it comes to calculating the time to the next reaction. Okay. So I kept on saying, okay, we're solving the chemical Langevin equation. The method we're using to solve the chemical Langevin equation is basically the weak trapezoidal rule. So this is a second order weak method, and this is basically, it's a two-step method. I mean, in principle, the original paper by by David, you kind of have, you can become also implicit. Here we just use the explicit version of it, okay? But basically, that's all it is in terms of the numeric, how to write down the numerical method. Are there any questions before I show you the nice pictures? Okay, some of those pictures are very nice. We're very happy, or at least I was very happy. I'm not sure about Radek, but I was very happy with these pictures. So, I presented 3 algorithms, and basically each of the numerical investigations has been done with one version of the algorithm. So, in particular, the exit time calculation that we're interested here, it relates with a birth-death process in which I kind of know a priori what is the upper bound for the number of molecules, so I can use this thinning approach. The other two, I'm using either the Gillespie one or the next reaction method one. So the first thing that we wanted to look is to see how well does our method work in terms of steady state calculations, okay? So what we were hoping to see, even though in some sense there is a difference, but the actual difference between the chemical Langevin equation and the SSA is not that pronounced. So what we wanted to see was, is our hybrid method capable of capturing the long time statistics, and also how does it compare with respect to SSA and chemical Langevin equation. So here I start with a Gaussian mixture. I have this chemical system. Okay, I start with a Gaussian mixture for the initial condition of A and B. Okay, and in this nice picture you just see what happens as you simulate the equation forwardly. Okay. Of course, when it comes to the chemical Langevin equation, I have to be a bit careful because I need to impose reflecting boundary conditions here. Otherwise, my solution would become negative. Okay, and as you see, basically they all kind of converge to a steady state. Okay, this is the steady state from the SSA. This is the steady state from the chemical Langevin equation, and this is the steady state from the hybrid system. Okay, so I mean, what I've done here is for a specific value of volume. What I want to do now is take different values of the system and study what happens to the first moment and the second moment, okay? And as you can see, the hybrid and the SSA method are agreeing completely, not only on large volume, but also on smaller volume. And in some sense, that's not very surprising, but it was kind of nice to see it happening, while here we see essentially what we discussed before. We said that the chemical Langevin equation is a good approximation of the large volume limit, but when the volume becomes smaller, basically it stops being such a good approximation. But when for example, the difference remains in the second moment, but it's not as pronounced as in the first moment. So in some sense, this was an interesting proof of concept in the sense that we basically we're basically as good as SSA, if you like, but then on the other hand, this is not the best example to show, because I mean, at the end of the day, there is not so much difference between the chemical Langevin equation and the SSA. Now, where it will become more pronounced is in the next two slides that the next two examples that we're gonna talk about. And I mean, I find one of those examples actually quite remarkable, and it is also going to be more pronounced when you're interested in exit time statistics. This is a well-known fact that the diffusion approximation might give you significantly different exit times than the continuous process. Okay, so now I'm looking at the local Volterra model. I mean, we're thinking of, okay, let's look at something that is a bit multi-scale in some sense, and see how we can apply how does that method works. Okay, so I mean, this is a Gillespie realization of the system. I have long bursts, and then I go down, and then up, and then down. So in that sense, we thought that the method that we're proposing, or the model that we're proposing, if you like, it would be very good in dealing with these things, because actually it doesn't need to know when the system is in large copy numbers or in small copy numbers. It kind of deals with it directly. And in some sense, this system is highly multi-scale. You see that you have things that are happening very quickly. Here, I'm basically plotting a one individual trajectory, and what I plot and what you see in the color bar here is basically the average number of chemical reactions that take place within a time step of delta t equals 10 to the minus 2 at a given state. So I have a lot of fast reactions here because I have large population. I have very much fewer reactions and sort of like slower reactions if you like. So the first thing that we did is basically on this one we wanted to compare what is the exit time behavior for the SSA and the hybrid model. Okay, so we basically I would need to look at the paper a bit more carefully, but I think we started somewhere like here or somewhere like here, and we asked how much time does it take to enter a specific area, and we did this comparing the SSA, and we also did this comparing SSA and hybrid model. Okay, so these are the histograms. Okay, so I do 10 to the third independent realization for each of the models, and this is what I get. And not only that, I mean I can do, and this is another thing that I kind of learned about. So okay, this is basically the problem from where I started. I started for 2,000 molecules of A and 5 molecules of B, and I asked how much time does it take starting from here to enter this domain. Okay, so this is how the first mean passage time statistics look like for the SSA and for the hybrid model. When I do the QQ plot, where basically I have, let's say, 1,000 realizations for the mean first passage time of the SSA and 1,000 realizations for the mean first passage time of the hybrid model. So if I order them, okay, I order from smaller to larger for SSA and for smaller to larger for the hybrid model, and I just plot them. Okay, I mean you would expect if these are coming from the same distribution that they would more or less be aligned along the y equals x axis, which is what we're seeing here. So in some sense, I mean both on this level and on this level, it seems that the hybrid model is doing a good thing. So trying to talk a bit about computational comparisons and which is kind of faster and which is kind of slower. First of all, I find this quite remarkable, but I mean maybe it's not. Maybe it's obvious to you. I mean, basically, what we're doing in this case, I'm just asking what is the expectation of A at some final time t. Okay. So this is how it changes as I change the final time t that I'm looking at, and you see the SSA and the hybrid model are always going together, and then you get something very interesting, or at least I find it interesting. In principle, we said that when you have the number of molecules being large, SSA and chemical Langevin equation are sort of equivalent in some sense. But here you don't see the whole picture. We don't really see what happens for B. So even though, you know, things are sort of like going up, yeah, for the true system, the chemical Langevin equation completely misses that, you know. And that basically has to do with getting the exit time for B, or you know, the B becomes negative, becomes smaller much quicker than it should do, and that sort of like drives A down instead of driving it up, basically. And in terms of comparing the average CPU time, this is basically what the chemical Langevin equation has. Basically, this is the cost. This is how much the computer was running for one individual realization. The SSA has that. And more or less, we're looking at the hybrid for placing the blending zone in different parts of the domain, and we see that more or less we have kind of the same cost. Okay, I mean you could argue, and you would be right to argue that, you know, when it would come to use the SSA, you would probably use some sort of, I mean, you know, the one is exact, the other one is not exact. So I mean, perhaps a better thing to do would be also to add a comparison with a tau leaping of form of the SSA. Okay, so in the last example, and then I'll stop. I'll basically just talk about the one-dimensional Berthet process. The point here is that I know a priori how big my system can be, which basically means that I can apply the thinning method that I sort of like skimmed through before. Okay, so and I'm interested how much time does it take if my process starts at n to hit 0, and basically this is the corresponding equation for the discrete process. This is the corresponding equation for the continuous process, and here is basically what our results gives us. So we're basically starting, we're using different parameters. K2 is the death rate. So K2 equals 4, 5, 6, 7, 8, 9, and every time I start my particle at either 4, 5, 6, 7, 8, 9, the birth process is equals to 1, and I ask how much time does it take to hit 0, basically. And on the left figure, I just have blending areas of size 1, and I keep on moving my blending area, putting it in different positions. And here I have blending areas of size 2. Okay. Basically, what you see is that when the blending area has size 1 and is very close to 0, I mean, I'm still sort of better than the chemical Langevin equation, but I'm not capturing the true behavior. But when we basically make the blending area to be equal to 2, basically the hybrid model agrees exactly with the SSA. And I think this is, I think this is definitely worth exploring more and trying to understand what is happening here a bit better in detail, in the sense that this might reveal you sort of like the important time scale in the model, because in some sense, away from 9, you just kind of treat things like you would treat a chemical. I mean, you know, away from 9, you kind of solve something like that, okay, with different boundary conditions, and it's basically only in you know, from 7 and onwards that you kind of treat the model closer to what the true dynamics are, if that makes sense. So to conclude, so I claim that we have defined a very simple procedure that provides a good approximation to the CME. I don't really need to know a priori the fast and the slow species. After proposing the model, we kind of talked about different ways to simulate. And in terms of future plans, I mean, we have already been discussing about this with Radek. We will try to apply these ideas in the context of stochastic reaction diffusion problems. I mean, another thing that you could do, even with this model, before you go spatial, is there is nothing that's stopping you from introducing an extra blending region when the number of particles becomes even larger, or when reactions become even faster, in which you treat things according to the reaction rate equations. So in that sense, you would kind of have sort of like something that can be simultaneously deterministic, continuous stochastic, and discrete stochastic, basically. Yeah, and this is basically something that I would like to discuss with people that they do parameter estimation, is perhaps try to use this model to perform approximate Bayesian computation for parameter inference. So thank you very much for your time and attention. So any questions? Or I mean, we can take a cup of tea as well. And
can you blend differently in different species? So say you have a lot of A molecules, very few B molecules. Can you put A in one regime, B in a different regime?
so in some sense, I haven't done complete justice of the thing. You shouldn't really be thinking of the blending happening on the level of, I mean, the blending, the right way to do it, we did it this way, but the right way to do it is to do it on the level of reactions. You do it on the level of reaction. So you say, if, you know, where here, I mean, I have the, so here where I have x in some sense, I shouldn't have x. I should sort of have the propensity function. And so in that sense, in that sense, so the system kind of checks, is that a fast reaction or is that a slow reaction? If it's a slow reaction, I will do it discretely. If it's a fast reaction, I will do it continuously, basically. So I would like to think that in this way the blending will take what you said into account, and in some sense it does. I mean, here part of the problem is, I mean, if in the Lotka Volterra is that, you know, these are not completely in phase. Yeah, you still have something being large while something else being small, but sort of like the hybrid model is able to get this directly. So without you having to having to tell it, and that's basically why you get this weird statistic here, that it goes down and then it goes up, because really the system, the continuous approximation fails because the number of B molecules becomes small, so it kind of moves faster, if you like, than what it should, and then this drives A down with it, basically. So I don't know if that's answering your question, but yeah.
Can you go back to your picture of the blended trajectory?
Yes.
I'm sorry if this is completely obvious and I'm just missing it, but if I'm in the blended region,
Yeah.
going around with my mix, you know, of diffusion, that one.
Yeah.
Imagine I'm at 4.5 and I do a jump to take me across your dash line, and now I'm at 3.5.
Here. No. Yeah.
Yeah. How do I get back onto being exactly integer value? Like if I want to have an extinction event that something goes to 0.
Well, when it comes to the propensity functions of the discrete part, they're not treating it as 3.5. They're treating it as either 3 or 4. So
go around it, or
you don't
in the propensity.
in the propensity functions you round it. Yeah, I mean that's basically why you cannot become negative. You see, this symbol here means
So
sort
the
of
population itself then could never hit 0, for example, in that case. A half would be the smallest it could hit or something.
no. It could become minus 0.1, and then you would call this 0. Yeah.
But the species counts could become minus 0.4.
Yeah,
That's what I'm trying to
understand.
Yeah.
Yeah. So actually, when
And it jumps by integers once you're in that region.
yes, exactly.
But you don't perturb it back onto an integer value.
No. I guess we could do that, but we didn't really see. I mean, you really need to do this.
I mean, that's introducing some other source of error.
Yeah.
Right? So what is the effect?
So you really need to do this if you want to make sure that you don't become negative. Because I mean, when I didn't do this in the first kind of when we were playing around with ideas, I kind of start having something becoming negative, and but then
And your scheme there is you just round it, or
yes, exactly. Any other questions?
not
Okay.
online questions, just offline.
Yes, offline questions. Okay, thank you.